Yes, hello everyone. My name is Toke. I'm a kernel engineer at Red Hat, and I decided to do this talk as a publicity stunt for the kernel RTNL mutex, which I am very happy to see so many people are interested in that. So I will talk a little bit. This comes from a customer escalation we had about 6 months ago. I will talk a little bit about what that entailed, and then I will talk about what the kernel RTNL mutex is and how you can debug it, and what this means for your networking applications and so on. So, as I said, I'm a kernel engineer at Red Hat since 2019, and this will tell you what the kernel RTNL mutex is, why you should care about it when you're writing applications. And the reason for this is if you're writing, so as I will tell you, this was an escalation that came out of someone writing an application that required consistent, really low latency, and that requires attention to a lot of details, including kernel internals, as we will see. So it's sort of a thing to keep in mind, have in your back pocket if you ever run into an issue that could be like this, and just sort of how do you structure your application to make sure that that you will always be able to control your sources of latency, basically. So, as I said, this all started with a customer escalation, which was deceptively simple. It was a 3-step description that we got from the customer. Create 2 pods on a Kubernetes cluster with several VFs, so virtual network functions inside each. Delete one of the pods, allowed to recreate, and the other pod will then miss heartbeat. So this sort of reveals the fact that even though we say pods and containers are logically separated from one another, they should be completely isolated. That was not the case in this instance. And obviously, if you have one application running that gets hiccups whenever you do something else in your cluster, you're not really getting the performance you wanted. So this was kicked up to engineering as an escalation, and it took a while to figure out what was this root cause, what was going on. So as a side note, to set the stage for what was going on, well, the RTNL mutex, what is it? So inside the Linux kernel, we have a lot of state about the network data path, all the control path things you do. So you configure physical and virtual network interfaces, you configure network namespaces, which is what we in Kubernetes land call pods. You have routes, you have neighbor entries, you have net filter rules, you have TC rules, you have qdiff, you have all these different objects that you can create inside the kernel through the various control planes. Most of it via netlink, but also, as we'll see, other configuration interfaces. And obviously, the kernel being one global monolithic application running at once, this needs to be kept consistent. And what do you do when you do parallel modifications of state to keep it consistent? Well, you have a mutex. And the kernel RTNL mutex is the name comes from the routing table netlink, which is the configuration protocol you go to user space with. And it has one big mutex that protects kernel state. And this is a little bit of an excerpt from the rtnetlink.c in the kernel source, which does basically this. Lock, figure out what we're trying to do it, unlock. Very simple, right? And then there's a lot of abstractions for which bit, what are you doing, what is do it, et cetera, et cetera. But that's not really important for this talk. So this is sort of the gist of it. We take the lock, do an operation, release the lock whenever we get a configuration thing from user space. The RTNL mutex is global for the entire system, with the caveat that there's ongoing work to reduce the scope because of issues like this. But historically, it's been global for the entire system. It helps during most configuration change operations, and some query operations will also take the lock to make sure that it gets consistent state. So, for example, if you're getting 2 different kinds of state, you can't just read it. And historically, it's easier to just take the lock, read, and query. So that means that any call that an application issues into the kernel can block on this lock. And since it's global, that means unrelated activity going on in other parts of the system can interfere with your application. And so, as you can probably guess, if we go back to the customer issue, we had this delete one of the parts thing as the trigger. So deleting a part, that's a kernel control plane thing. So maybe we were seeing an RTNL issue. And that's kind of a hunch to start looking into, but it was still hard because it was a thing running on a cluster and was not deterministic as these timeouts usually are. So we were like, okay, there's thousands of these, which one is it? Finally, we got a reproducer from the customer, which is like something that iterates, and it usually gets around 100 to 200 milliseconds of latency, and then suddenly, boom, goes up to 3 seconds, which was not good for them. And the code that was doing this was basically just a loop around this little thing. It was trying to query a MAC address from the kernel neighbor table, and there's this ioctl, which, as I said, not everything is netlink. And it was doing this SIOCD ARP operation through an ioctl. And if we go into the kernel and see what is this ioctl doing, well, this is from kernel 6.10 and older. It is taking the RTNL log, figuring out which of these commands, this was the one we were doing the request, and unlocking. So here was our culprit. We had an operation that was just querying state from the kernel, but because of the way it was implemented, we were still taking the RTNL to do it. So what can you do to look at this? Well, we have this tool, klogstat, which is part of libbpf tools from BCC. So the BCC utilities is a repository of various utilities originally written in Python, which uses BPF to poke into internals of the kernel and pull out lots of different state. And originally, as I said, everything was in Python, but it has now gained some utilities that are pre-compiled, which is in the libbpf subdirectory of the repository, and it's also packaged for Fedora and RHEL as libbpf tool. And the utility I will show some examples from is called klogstat, which will go in and attach trace points to the mutex lock and unlock inside the kernel, and then it will tell you what is actually holding this, which applications are waiting for it, and so on. So you can use this to examine the RTNL usage. So this is the command line to run for 30 seconds, only look at the RTNL mutex, and -p is show which processes are involved. And I just ran this on my laptop as an example, and you can see these are the different application names like you would get from PS, and this is how long they're waiting, and how many times they're waiting, so the total time they spent waiting on this application. So this was, so these are the wait times, and these are the hold times. So here you can see which applications are holding it. So what I did here while I was doing this is these are applications that are running on my system and regularly querying the state of the kernel network. And IP was the application I was just using to create and tear down a virtual Ethernet device. So that means that the IP binary, as you can see, that will hold, in this case, only for 11 milliseconds, the longest. And that turns into wait times for some of the other applications. So that's sort of the basic usage. You can say, OK, which application is querying this lock? If you don't limit it to one lock, you will get every lock in the system, which can be a bit big. But if you don't know what you're looking for, this can be useful. You can also, if you don't do the P, you will get some statistics just for the locks and not for the processes that are involved. Then it will also show you, this is if you remove the P. So which kernel functions are involved here. So you figure out, OK, this application was holding this particular lock, but why is it doing this? What's going on? And in this case, you can see which kernel functions are immediately calling into the lock. So in this case, we have some link watch events receive message. RT netlink receive message is a pretty common one because that's the function that takes, that passes the netlink message that comes from user space and does something with it. Similarly, RTNL dump it is the function that will create a user space netlink message and send it to user space for things. And down here, it's a bit more specific. The functions that was holding the lock, this is again from IP as before. It was creating a link or it was deleting a link. So I was doing, like this ran for 30 seconds. So I was sort of creating a link and deleting it again. So here you can see, okay, this is what's holding it. That's pretty easy. I can go and do something for this. But these up here, okay, something is dumping some information to user space. Something is receiving a message. That's not so useful. So after having this whole thing with an escalation, I have to figure out which application is doing it. We went in and did some improvements to this tool to add some more information. So, so this is, now I'm looking at a particular PID, and I say I want 5 levels of kernel stack trace for what's going on here. And then you can see, then this will output a lot of data, so I've just picked out one particular stack trace. So this will give you the whole call trace. It goes netlink, blah, 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 all the way up to netlink receive message. But it still doesn't tell you what is this receive message actually doing. So what I added for this was you can see which log it is down here, and now you can also see the command that was sent via netlink. So that gives you not just, okay, this is a netlink operation, which a lot of things are, but you can also say, this is the getlink netlink operation. So that gives you a bit more information of what is actually going on. Similarly, if you're doing an ioctl with ETH tool, for example, it will also store which ioctl is it doing. This is available since BCC tools 0.34, so that's a few months ago that was released, which is why this is compiled from source. That's why the command line is different here. So with this, you can go and poke into what is actually holding this lock if you run into a stall based on this lock, like we did. So what can you do if you find out that your application is blocking on this? So the reason that the original customer issue here appeared was that they were doing this as part of their latency-sensitive applications. So the thing you want to do when you are writing an application that queries kernel state is to move it out of the fast path. So be aware of this. Anything that queries kernel state, anything that that issues a sys call, you have to be aware, is this sys call something that can block? This may be hidden in libraries. You can use klogstat, other utilities. There's other bunch of stuff in BCC tools that can query kernel state like this. If you want further information, you can also use the BPF trace utility to try to trace the application in more detail. And if you find something that involves the RTNL, for example, what you can do is you can move it out of the critical path in a separate thread, for example, so it can block, and then you can propagate the state to your application. That means the data may be out of date until the next query, but you won't block. So this is a trade-off, obviously, you have to do for your application, but these are the kinds of mitigation strategies that you can have. And again, so there's work ongoing to limit the scope of the RTNL lock, but blocking is normal kernel behavior. So that's sort of the main takeaway I want you to get from this talk is don't assume that the kernel will always respond to you in finite or predictable time. Make sure that you structure your application so that you can deal with blocking. So what did we do with the customer case? In this case, well, there was actually a commit already where someone else had found this. This was, as I said, there's an ongoing effort to try to limit the scope of the RTNL. And one of the techniques that we use for this is that we have this thing called RCU in the kernel, which, if you're interested, it's a technique to avoid blocking readers of data by strategically doing atomic updates of pointers, so that you combined with a way of waiting on the operation to finish before we free any memory. So you can get lock-free operations for many read operations, which is also the case here. And in this case, this was the SIOCG ARP ioctl that is converted to avoid locking the RTNL. And with this, we basically fixed the issue for this particular customer. But again, we can't always do this. Like when you find something that's blocking in the RTNL, you can try talking to your local friendly kernel hacker and asking them if it's possible to move it around. But even with limiting the scope, so a lot of the stuff that is being done to limit the scope of the RTNL turns it into a per namespace lock, so that different parts won't interfere with each other. But inside that namespace, you will still have this interference. So depending on how your application is structured, you can still be hit by this. Oh, I'm going way too fast. Okay, so the key takeaway, the RTNL mutex blocking is normal kernel behavior. It's outside of the application control. We do have ongoing work to narrow the scope, but it's not going to go away entirely. Yeah. So, questions, discussions. I can go into some more details, but I don't have slides for that. But please go ahead.
Should I expect that reading the network device statistics from /proc/whatever will take that long?
So the question is reading statistics from the proc file system for network devices, whether or not that will take this lock. I think that statistics are one of the things that have moved to RCU, but I don't know off the top of my head. But yes, so proc file systems, sysfs file systems, all these virtual file systems, consider them syscalls. So I would suggest trying it with klockstat and see if your application triggers one of the locks to be sure. But again, just reading from a virtual file can very well call into this. So that's also something to be aware of. Yes?
Does klockstat provide machine readable format, dumping to a JSON file or dumping the quality data so that it can be processed later?
So the question is, does klockstat allow dumping the output to JSON so you can process it later? Or some machine-readable format? Oh, that's a good question. I don't recall. Yeah, sorry. I have not had a need for this, but it's not that complicated of a BPF program. So if there's a need for this, it should be. So it's sort of the way klockstat works is that it will install BPF probes on mutex lock on lock, and then there's a user-space daemon that reads this. And dumping that into JSON is definitely possible. So, but I don't know if the utility itself has that. No. Yes?
More of a comment. I had another customer case where the application was doing it was resolving a DNS name, calling get address info, standard UAC function. And that surprised me that also to RTNL, I think it enumerates the interfaces and the system. For some reason, that was a bit unexpected.
Yeah. So the comment was that you had an application that was just resolving DNS names, and that also ended up blocking on the RTNL. Do you know why? Yeah, another. Yes, so this is in glibc, right? Yeah. Okay, so let me see if I can repeat that. So I think basically the issue is that the DNS standard requires you to sort addresses depending on the addresses that are configured on the system, right? Is that it? So, yes. Oh, okay, yes. Yes, so there's an RFC for the get address info operation, which requires you to sort addresses. And to do that, you need to query the kernel on what addresses are available on all the interfaces, basically. Is that it? So that means resolving a DNS packet does this. Okay. Yes, that is, yeah. So something to be aware of, I guess. That one seems a bit harder to resolve, but I guess you will have to go by the same mechanism, make sure you don't block other operations while you're waiting for this. Yes?
Is there any documentation for user space programmers how to find which host should be this kind of block and which are safe?
Yeah, good. Yeah. Great question. So the question was, where's the documentation that tells a user space developer which calls will block and which won't? And all the kernel engineers in the room are snickering. So, so unfortunately, that's because the answer is no. There's no documentation for this, which is why I'm doing this talk. So something like klogstadt will tell you. So go and use that. Be aware that it's something that can happen. Is I think also like this is an awareness campaign, right? So just being aware that this is something you have to watch out for is a good first step. But no, unfortunately, we don't have a full documentation of all the places this is, other than reading this.
There was a recommendation to store address, but you need to know before this is the.
Yes. So I would say any operation that's not just sending or receiving data on an established connection, I would be paranoid about. But I don't know. I don't write enough user space code to have an idea of what. But so the utility here will tell you which logs it's taking, even if they're held for a very short time. So it's not just something you can use to debug a stalling issue. You can also run this and then do the operation on your application and say, please look at this PID like I was doing here, and it will tell you which logs were taken. You can do this like if you get rid of the RTNL mutex, it will tell you any log in the kernel that your application hits while it's running. So it's a very powerful tool to get information out. So I would recommend playing around with it and like the BCC tools, libbpf tools have a lot of these sort of let's look into the internals of the kernel. There's one that tells you if the scheduler spends too long, if your application waits too long on the scheduler. There's things to tell you how much queuing do you have in your TCP socket, all these kind of sort of weird kernel internal tools that you can just run, and it will give you some data to look at. Yes?
Would it make sense to replace the log with a redirect semaphore?
The question was, would it make sense to replace the log with a read-write semaphore? I think the direction it's going in is more to narrow the scope of the log, because I think I'm not a logging expert in this sense, but I think the read-write semaphore has some other overhead that doesn't make this. But Jiri would like to run with.
It cannot help because the problem is if you have write operation like creating a pod, it will take a write log, and you cannot take a read log while something is holding the write log.
Yeah. Okay. Yes. Yes. Yeah. So yeah, to repeat that. So a read-write semaphore would help with two readers not interfering with each other, but a lot of these cases, it's a write operation that's blocking you. So a read-write lock would still take a write operation. Yes, thank you, Jerry. So the way to avoid blocking is basically what this commit was doing, to move to RCU for things where you only query. In a lot of cases, this can be done for query operations, but sometimes you still need to do modify operations. And the other thing is then narrowing the scope. I can also add, the reason the customer ran into this was that they were using a network driver that was doing a lot of operations just for tearing down an interface. So I counted up to 3,000 synchronization operations in a single interface down operation for this particular driver. So that's obviously a bit extreme, but for some things that can, like the blocking here is not just 3 seconds. You can have 30 seconds of blocking if there's a lot of stuff going on in the system. So this like, and as you get more CPUs on the system, this only becomes worse. So it's sort of an ongoing thing, but it will not go away entirely. Yes?
Not to comment that obviously the write operations are very hard to solve, right? But there are use cases where you do lots of reads. For example, in my use case, I'm setting the network statistics every millisecond, and if DNS is interfering with it just by doing DNS spreading, obviously,
Yes.
just solving the read-only path would be a big way because
Yes.
it wouldn't interfere.
Yes, so the comment was there are use cases that do query operations at a very high rate by design, and the kernel should do its best not to interfere with these, especially other read operations. And I think we had a discussion at DevConf, I think, a couple of years ago about a very low overhead for statistics, specifically a new interface to make reading statistics basically just a memory read and not taking any locks, and that would give you, I think it would give you eventual consistency, but you wouldn't be blocking exactly for that reason. I have written applications as well that try to poll statistics very quickly. I don't think that ever went anywhere, but yeah, please share details of your application offline, and I will be happy to hear more about it. And for the read operations, moving things to RCU is also an ongoing. If you have a particular application that's impacted by this, we would, as kernel engineers, also love to hear about it. So that's also part of my part of the reason for doing this talk is to making people aware of it and also sort of directing the effort. So there's this ongoing thing. Yes, we want to reduce the scope, but how can we do this with the highest impact areas first? So if you have an application that's impacted by this, please let us know. And we can tell you if it's an easy fix like this or if it's a longer effort, but sort of knowing which are the important applications to focus on is very interesting for us as kernel engineers. Right? Yes, Jerry.
What are the next steps in upstream in removing or breaking up the RTNL?
Yes. So there is basically repeat the question. What is the question was, what are the next steps upstream in narrowing the scope or removing this lock? And there's basically two ways we do this, three. There was us moving things to RCU when we can, is the easy one, but that's only for simple cases of querying things. The other thing is there's a per namespace lock being added. So instead of having a global RTNL lock, we will have one per namespace, which will make sure that namespaces don't interfere with each other. And the other thing that's being added is a per device lock, which for operations related to only that device. So it's all about making it more granular. And of course, as with anything Linux kernel, it's a little bit this, we are replacing the wings on the airplane while we're flying it. And combined with locking, it's very finicky, but we're trying to add the new lock, there's already been patches posted for a lot of this, and those add the new lock, but hide them, but still keep the RTNL, so that we can have more granular locking added incrementally, and then at some point, when the maintainers feel that this is stable enough, we will flip the default to get rid of the RTNL. I believe that's basically the plan. And right now, some of these initial patches that are in, they're hidden behind a config option, and if you turn that on, sysbot goes crazy and finds all kinds of locking issues. So it's still like a bit of the bigger effort is very much a work in progress, which is why it's not finished. We also had discussions on how are we going to deal with this in RHEL, which will also be interesting. But for now, it's the upstream effort is about making sure that this lands and becomes stable enough that we can rely on this and get rid of the RTNL. All right. That got us a bit closer to the allotted time. Any further questions? We still have a few minutes if anyone has further thoughts. Otherwise, thank you for listening to my publicity stunt for a lock. That was fun. Thank you very much.